In this video, we're going to work through some additional examples where we're going to try to find fixed points of a system and then check to see if they are stable. We're going to strip away some of the modeling aspects just to make sure we understand the mechanics of this for now. So let's consider a generic difference equation. an plus 1 equals 2 plus 3an minus an squared. And let's find the fixed points and check which one or ones are stable. Okay, so to remind you, a fixed point satisfies a star equals g of a star, where in this case, the right-hand side is just the g that we're interested in. So we can call that g of an. And stable, so that's tells you that a star is a fixed point, or an equilibrium point is another name for it. Alternatively, if we want to know that it's stable, then g prime of a star less than 1 tells us that a star is stable. All right, so that's the background information we need to solve this problem. Let's go about doing that. So our difference equation is has g of a star as this polynomial. And so let's try to figure out where that equation is satisfied. So we'll have a star equals 2 plus 3 a star minus a star squared. And if we were to bring the a star over to the other side, this would be 0 equals 2 plus 4a star minus a star squared. And that is a quadratic equation. If we want to find the solutions, we could use the quadratic formula. And that would be, let's see, a star has got to be equal to minus b, which is the coefficient of the first power term. So minus 4 plus or minus the square root of b squared minus 4 times a. And in the quadratic formula, a represents the coefficient of the squared term. So there's a negative 1 in front of a star squared times c, which is 2, all over 2 times a. And in this case, we will have minus 4 plus or minus the square root of 16 plus 8 all over negative 2. Or we could write that as negative, the 4 we could place over the 2, and that would be just a 2 plus or minus the square root of 24 over 2. And notice I've dropped the minus from the denominator because plus or minus encompasses, well, both signs. And so whether I include the minus or not, that just changes the order, and that order is really not relevant. All right, so those are our fixed points. And we could simplify that a little further if we wanted to factor out that 24. 24 is 4 times 6. So we could write this as square root of 24 is just 2 times root 6. And so this is 2 plus or minus root 6. And as a decimal, 2 plus square root of 6 is around 4.45. And if we do minus square root of 6, we'll have around minus 0.45. Okay, so those are our fixed points. We're trying to solve where a star equals g of a star, and just basically using some of the familiar algebraic techniques from previous courses. And so we found 2 fixed points, and now we'd like to know if they are stable. And so to do that, we will compute the derivative. We need to look at g prime of a star. And so g of a was the right-hand side of our equation. That was just 2 plus 3a minus a squared. So g prime of a would be 3 minus 2a. And so we'll take those fixed points one by one. G prime of 4.45 is equal to 3 minus 2 times 4.45, which would be 3 minus 8.9, which would be negative 5.9 absolute value, or 5.9. And G prime of negative 0.45 would be 3 minus 2 times negative 0.45, which is absolute value of 3.9. And notice that both of those are greater than 1. So this is, so both fixed points are unstable. Great. So in this case, we found values greater than 1, so they're unstable. But if you find a fixed point that has a derivative that is less than 1 in absolute value, you would conclude that it is stable. And if it's equal to 1, that is a boundary case. It is not clear. This test would be inconclusive, and you need to use some other method. And we're not likely to encounter those cases very often, so we won't worry so much about that at the moment.